Hi everyone, welcome to our presentation, a 64-bit ARM CPU at cryogenic temperatures, design technology co-optimization for power and performance. I am Rakshith Saligram. I have Divya Prasad, David Pietromonaco, Arijit Raychowdhury, and Brian Cline as my co-authors for this paper. This work was done as a part of internship program at ARM. A little bit about myself. I am a graduate research assistant at the School of Electrical and Computer Engineering at Georgia Tech. I am the third year of my PhD program. I have a master's in electrical engineering from University of Southern California, Los Angeles. My current research interests include cryogenic computing and VLSI systems and quantum devices and circuits. This is the outline of today's talk. With the general introduction of today's computing situation, we will start with cryogenic CMOS and its benefits and why we need this benchmarking study. We will then go over different benchmarking flows that have been used in this work. We will examine some of the key results and demonstrate via simulation study the other benefits of cryogenic CMOS. Conclusions and references follow. Compute demand has grown over 100x within the last decade and has well surpassed the growth in classical Moore's law's transistor density, as seen in this graph showing transistor density growth rate and high-performance computing peak transactions per second uptick for the last few years. The transistor dimensions laterally shrank from 10 micrometer in 1970s to around 22 nanometer in 2010. Short channel effects like interface scattering, dibble, etc. made transistor operation in a desired way harder, which was then alleviated by FinFETs and other non-planar technologies. While we are at the brink of what lithographic process can achieve, and even what techniques like fin depopulation can provide, we can say that the dimension scaling has been plateaued. The shrinking of the wire dimensions, which causes the resistance to increase exponentially, makes matters worse. The modern day microprocessor designs are equally limited by transistor and wire performance. In this graph, we try to break down the average critical path delay of a microprocessor into its constituent components across different generations of devices, and we observe that the sum of RW and CW and RW and CG components contribute to around 50% of the delay. Thus, we need advancement in both transistor technology and interconnect technology to meet the HPC demands. Cryo-CMOS computing or low-temperature CMOS has been studied as a potential for achieving the above said advancements. At low temperature, two main opposing effects act together. One, the transistor threshold voltage increases due to Fermi potential shift and band gap widening, and two, the transistor charge carrier mobility increases. We know that the device off current is proportional to the negative exponential of the VTH. Thus, the off current decreases exponentially as we reduce the temperature. The carrier mobility controls the device on current. Thus, as we reduce the temperature, the current on-off ratio increases, which means subthreshold swing improves. We also see that the drain and the source resistances improve. While the above changes are seen on the transistor side, on the interconnects, we know that the bulk resistivity of metal wires decreases as we decrease the temperature. Thus, the metal wire resistance improves. Despite the increase in threshold voltage, the overall performance measured in terms of the device on currents shown improvements, and additional boost can be obtained with appropriate process changes. By process changes, here we mean tuning of the threshold voltage, which we will see shortly. There have been numerous research and articles showing betterment of devices at transistor level and some at the circuit level. We can safely say that most of us acknowledge the benefits of cryo-cooled CMOS at device level, but we need to understand if the same benefits translate to system level. Thus, we need to evaluate the overall system level benefits of low temperature CMOS. Therefore, we need a benchmarking study to quantify the performance benefits of low temperature CMOS, which is done in this research study where we benchmark a 64-bit high efficiency Arm Cortex A53 core by carrying out technology co-optimization. In this first flow, we will see how we optimize the technology. For device modeling, we utilize an open source MIT virtual source model framework and calibrate them to Foundry Gen 1 FinFET room temperature IVCV data. This will establish the room temperature device models. Next, we obtain the temperature dependence of different transistor parameters from measured experiments from University of Notre Dame and use it in conjunction with the room temperature device models to obtain low temperature device models. Let us say, for instance, 200 Kelvin. If the device off currents at 200 Kelvin match that of the room temperature device, then the model quantifies as the iso leakage model at 200 Kelvin. If not, we adjust the threshold voltage and regenerate the models for 200 Kelvin. We repeat this experiment for different temperatures of 100, 150, and 200 Kelvin and different supply voltages of 0.4, 0.6, and 0.8 volts. What we see in this graph is that at a nominal supply voltage of 0.8 volts, a device on current measured on the iso leakage device models increases by 32% at 200 Kelvin, 55% at 150 Kelvin, and 68% at 100 Kelvin. This improvement at 100 Kelvin is actually greater than 3 times the typical 20% improvement in saturation current expected from node-to-node scaling by Moore's law. Next, we will go about the wire resistance calibration. We start with the open source room temperature wire resistance model, including Maeda Schottky's and Fuchs model to capture the size effects of copper. We then calibrate it to Gen 1 FinFET Foundry PDK room temperature resistance data for all the backend offline layers. The models are then extended to low temperature. The total copper resistivity comprises of two components: a temperature-independent component due to size effects, which include surface scattering and grain boundary scattering, and the temperature-dependent bulk resistivity of copper. In this graph, we see the improvements in the resistivity of local, intermediate, and global interconnects. Higher metal layers have smaller size effect components than lower layers. Thus, we see larger improvements of 21% in the resistivity of global metal layers, that is M8 and above, than the local metal layers, which is around 18%. Next, we look at the standard cell characterization flow. Production grade 9-track standard cell library with low VTH flavor are re-characterized at multiple VDD and temperatures using industry standard tools. In our case, the flow is modified as below. For a given temperature and VDD, we have the iso leakage device models along with the RC models for the BEOL stack. We use these in the FinFET Gen 1 PDK library schematic and layouts to perform parasitic extraction and then run standard cell recharacterization flows to obtain standard cell library for that VDD and temperature. We repeat the flow for different supplies of 0.4, 0.6, and 0.8 volts, and for 4 temperature points of 100, 150, 200, and 300 Kelvin. We try to calculate the average rise and fall delays of all the cells in the standard cell library at a nominal supply voltage of 0.8 volts across all the temperature points. We see up to 38% improvement in the delay compared to room temperature. This is almost 3x better than what we obtain from technology scaling from Gen 1 FinFET to Gen 2 FinFET. We notice one other effect. When we look at the normalized input pin capacitance of all the cells in the standard cell library, we notice that it increases by around 11 to 14% at 100 Kelvin compared to 300 Kelvin. This is due to the fact that lower threshold devices have higher charge accumulated for the same supply voltage applied across them. We will see why this is relevant in a couple of minutes. Once we have all the essential ingredients for auto place and route, we go through the following flow. We implement the Arm code with generated standard cell library and BEOL metal stack by initially synthesizing it. Suitable floor plan is chosen to keep the cell density at optimum levels. We design the power delivery network using Arm PDN design methodology. We place the design, we perform clock tree synthesis, do signal routing and optimization, and finally analyze the database for power and performance. Initially, we did this for a nominal supply voltage of 0.8 volts for all the 4 temperature points. Later, we optimized the supply to 2 other values of 0.4 and 0.6 volts and reran the experiments. Some of the key benchmarking results are shown here. The first case is the peak performance analysis at nominal supply voltage of 0.8 volt. We find the maximum frequency that a design can operate at each of the temperature points. We see 16% improvement at 200 Kelvin, 33% improvement at 150 Kelvin, and 56% improvement at 100 Kelvin compared to room temperature. However, this comes with more than 2x increase in the power dissipation. Analysis showed that the dynamic power increase was due to higher operating frequency and higher switching capacitance. The higher switching capacitance is due to increase in the input gate capacitance of lower VT devices, upsizing of the gates at higher frequency, and more buffering to address the hold violations. The increase in the switching capacitance of the design across temperature, along with a normalized increase in the operating frequency, is shown in the graph here. The increase in the internal power was due to the increase in the peak value of the short circuit current at lower temperature due to large overdrive voltage created by low VT devices. We expect that if this design is implemented using multi-VT standard cells for non-critical paths, then the increase in the power at low temperature will reduce. I would also like to point out that the performance improvement at the core level surpasses that at the logic gates, which was 1.38x, which can be attributed to BEOL RC improvements and EDA optimization. We take a second approach to take the advantage of increased voltage overdrive at lower temperature. So we reduce the supply voltage and analyze the peak performance at new VDD. We see around 1.87x improvement in the peak frequency of operation at 100 Kelvin at 0.6 volts VDD compared to the room temperature design of 0.6 volts. We try to do the same at 0.4 volts VDD, but the devices can't operate at 0.4 volt supply at 300 Kelvin, so we do not show any improvements in the last case. An obvious observation is that the peak frequency at a given temperature decreases as we decrease the supply voltage. Next, we draw the performance per watt improvement versus the performance at 4 temperature points. The corresponding supply voltages are annotated. Any line parallel to the y-axis will denote ISO performance line. We notice that at 0.8 volt room temperature frequency can be achieved at 200 Kelvin with 2x lower power, and 150 Kelvin with 3x lower power, and 100 Kelvin with 3.7x lower power. Similarly, the 0.6 volts room temperature frequency can be achieved at 200 Kelvin with 3.2x lower power, and at 150 Kelvin with 4.1x lower power. Thus, we show that the cryo-cooled CMOS systems can achieve either higher performance, which comes at a cost of higher power, or can be optimized to achieve higher power efficiency in terms of performance per watt. Next, we look at the additional benefits we obtain by performing computing at cryogenic temperature. Modern day microprocessors are performance limited due to substantial increase in the junction temperatures, mandating frequency throttling for reliable operation. The graph here shows the variation of thermal conductivity of bulk silicon across temperature. At 300 Kelvin, it is around 0.13 milliwatt per micrometer Celsius, while that at 100 Kelvin is 1 milliwatt per micrometer Celsius. The thermal conductivity of bulk silicon increases by almost 10x at 100 Kelvin compared to room temperature. Therefore, bulk silicon, where most of the heat dissipation occurs, which shows a rise in temperature, now acts as good as a copper conductor in heat conduction at 100 Kelvin, alleviating self-heating effects on the die. This means that the heat removal from the chips will be much easier at 100 Kelvin. This material level benefits need to be quantified at the system level for thermal implications. We compare the rise in the junction temperature for 298 Kelvin and 100 Kelvin designs. To better capture the self-heating effects, we consider the design of an ARM server high-performance core implemented using Gen 2 FinFET technology functioning at maximum power workload benchmark program. The design is divided into fine mesh, and the average temperature for all points in that mesh is computed and to obtain the temperature in that mesh. This will yield the heat maps for the design. We use industry standard tool Cadence Celsius for this analysis. Initially, when we look at the 298 Kelvin heat maps, the low temperature of the chip is 298.6 and the highest temperature is 303.3 Kelvin, giving the rise in the junction temperature delta T as 4.7 degrees. We change only the thermal conductivity of bulk silicon to 1 milliwatt per micrometer Celsius and the operating temperature to 100 Kelvin and obtain the heat map. Now we notice that the lowest temperature is 100.9 Kelvin and the highest point is 102. This will make the rise in the junction temperature as 1.1 degrees. Thus, we see more than 4x reduction in the junction temperature rise from 298 Kelvin to 100 Kelvin. Hence, we can infer that higher number of processors can be packed together at cryogenic temperature while still adhering to the same thermal design power limit or the TDP limit. On the concluding lines, this is, to our knowledge, the first system-level showcase of benefits of low-temperature CMOS for high-performance computing. We calibrate the room temperature device and wire models to Foundry Gen 1 FinFET PDK and extend to re-characterize the production-grade standard cell library, each consisting of around 550 cells for 4 different temperature points and 3 supply voltages, giving a total of 12 standard cell libraries being re-characterized. We perform APR and analyze the power performance to show that with cryogenic cooling, we can obtain 1.56x performance boost compared to room temperature at 0.8 volts VDD and 100 Kelvin, or we can achieve 4x improvement in performance per watt compared to 0.6 volts room temperature design at 0.4 volts and 150 Kelvin. And we also get 4x reduction in the maximum junction temperature rise at 100 Kelvin. Thus, cryogenic CMOS systems can provide multiple generation of Moore's law advancements. We would like to thank Professor Suman Datta and Vriddhi Chakraborty from University of Notre Dame and product teams at ARM. These are some of the references that have been used in this paper. Thank you.